Good afternoon, it's Jeremy. It's Tuesday, January the 21st, and we're in a polar vortex here in Toronto. It's really cold. It's at least minus 20 outside, not to mention the wind chill. I wish I was on a beach in Brazil with a caipirinha in hand. Today I want to talk about the Si5351. There's the development board, and I've had a few videos about this, about 4 videos, and I want to look at a GNU Radio model of it. So there's the dev board, and that's clock 0, clock 1, and clock 2. And I've got coaxial cables on clock 0 and clock 1, and they go to a picoscope, a digital USB scope. And notice I've got them terminated in 50 ohms because they're transmission lines. So I'm going to look at it on the scope and the spectrum analyzer, and we're going to compare that to the simulation. And there's the dev board is connected to the Arduino Uno. There's the 5 volt, and sorry, that's the SCL and SDA connection for I2C. And I've got 5 volts and ground over there. There's the USB for the Arduino, and then I've got the USB for the picoscope. So I'm going to go over to Camtasia, and we'll look at what we get.
Okay, so this is the Arduino code that we're running here to run on the 5351. Basically, it's just from the library. If you look under examples and you download the library, there it is there, the 5351 library. So I'm just using the first program there, and I've run it, and then on the serial monitor at 9600 baud, we can see that on clock 0 we got 112.5. At clock 1 I've got 13.5 megahertz, and clock 2 I've got 10.76. So I've got this connected to channel 1 on the picoscope. So let's go over to the picoscope, the digital scope, and there's my spectrum there. So there's our primary component at around 10 kilohertz, and there's my third component there at around 30 kilohertz, and there's my fifth component. What I've done is I've lined up the rulers on the third and the fifth to measure the dB. The scale is in dB. So the primary component is minus 0.5 dB, and the third component is minus 10. So when you subtract the two, you get a difference of 9.5 dB. And then when you subtract this from the fifth, you get a difference of 14 dB. So that's the difference in the components there. The reason we're looking at the square wave is that traditionally when you had a VFO, an amateur radio, you would use some form of a tube or a transistor or an FET or an NPN with a feedback, an LC feedback, adjustable L or adjustable C, and that would give you a sine wave output. But if you're going to use the clock chip in that type of a mode as a modulator or a demodulator, then you have to consider the fact that the square wave does have the component you want, which is the primary component, but it does have all the other odd components as well. Let's go into GNU Radio. So here's my simple model for simulation for GNU Radio. I'm just using the standard sample rate of 32K. And just for simplicity, I'm using a square wave source at 1K. Whether I use 1K or 10K doesn't really matter. You just have to up the sample rate, but I just picked it at 1K, and I gave it an amplitude of 1. I'm using a range variable for the amplitude. What I'm going to do with the amplitude is I'm going to vary it till the first component goes to 0 dB, and then I can directly read the difference between the third and the fifth. So let's run this and see what happens. So there we are there. There's a scope and there's a spectrum analyzer. So there's my range variable. I'm going to up this till down here, till there's the DC component. Notice it shows up as well. So there's my primary component. So I think if I go to 8.8, I think it is. Yeah, 8.8. The primary component is exactly 0 dB. And if I go down here to the third component, it's around minus 9.5, which is what the theory predicts, and the fifth component down here is at minus 14, which is exactly what the theory says. So that's the GNU model.